Hello everyone. Let's talk about continuous distributions. So you're already familiar with the normal distribution and the uniform, but now let's talk about them in general, the family of all possible normal distributions. So for different parameters of the mean and the standard deviation, the set of all possible uniform distributions. And then there's a few more. Okay, so the exponential distribution, as you can see, is describes the waiting time between events. So if events occur at random, this is how long you have to wait for the event to occur. And the t distribution, the chi-square, and the Fisher f distribution, these are rather specific. We'll need them in statistics. They're called sampling distribution. So they describe the distribution of certain statistics that we use for hypothesis testing and confidence intervals. So in chapter 2, you're not supposed to know about the statistic stuff. We're just learning them as basic building blocks. And so rather than, so this time we start straight away with the computer models. So for each math expression, there is a computer model from SciPy Stats. Heads up, the model, the t distribution family is called t, but we're going to alias import it as t-dist, just to a view of, because sometimes t will be the value of a statistic. It will be a number we compute. So we always import distributions, the ones that are ambiguous, like t, f, gamma, and beta. I'm going to import them in the code example as beta dist, gamma dist, t dist, and f dist. So in case you're looking at the code and there's like a t dist, it's t alias imported as t dist. Okay. The whole section, so 2.6 is just an inventory, right? So there is for each distribution, we show the function, the probability density function, its properties, and a few examples. So very similar to what we did in section 2.3. We're just showing the vocabulary of things you need to know. Exponential, normal, standard normal. So this is for an arbitrary mean and standard deviation. This is when the mean is 0 and standard deviation 1. Okay. The notebook is highly recommended. You can play with each function, gives you an example. So this is for the parameter 7. And I encourage you to change the parameter and play, just update, see what happens when you change the parameter. Okay. Okay, so then we reach a little math stuff. So the gamma function will appear in several equations in this section. And I don't want you to be scared of it. So we have a little intro. This is like an exposure therapy to a big Greek letter, capital Greek letter gamma. Intuitively, like I'll let you read, but the gamma function and the factorial are closely related. What the factorial does for integers, gamma allows us to do continuously. So for integer values, the gamma function and the factorial are equal. Here is the equation. The gamma of a number is the factorial of n minus 1. But then you cannot compute the factorial of 4.1, but you can compute the gamma of 5.1. So that's the difference, that factorial breaks versus this should be here. All right. And this is what the graph looks like. Okay, so why we talk about this, because if you look at students t distribution, there's a gamma factor in here. Do you really need to know this? No. We're gonna use the computer model for most of the calculations with the student t distribution, but you know, if I want to show you the formula, I have to explain what this is. So that's students t distribution. Okay, this is very important. If you look at, so the dot 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 is the highest degrees of freedom. So that's the parameter nu. The dot 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 is roughly, it looks very similar to a normal distribution. So there's a peak in the middle and then it drops off. After 2 standard deviations, after 3 standard deviations, it's really dropped off a lot. Now, as nu, the degrees of freedom decreases, we get the other curves, so the green curve here. So the peak decreases a little bit, and what happens is the extra weight goes in the tail. So we have a little bit here more weight. And then same for the yellow, I don't know what this teal color. And then the blue is the 2 degrees of freedom. That's so it decreased in height, and the tail got really, really heavy. Look, we're even losing 5 standard deviations away and there's still some weight. I mean, it's very little, but okay. So this is a principal example, like students t distribution will come up a lot in statistics. And the idea is that the normal distribution is very pessimistic. Once you go 2-3 standard deviations away from the mean, it says these events are impossible. This should never happen. And students t distribution is like, yeah, actually, you know, 3 standard deviations, it has some non-zero probability. The technical term or the informal term for this is to say the distribution has heavy tail. So there's more weight far away from the mean. And the parameter nu determines the heaviness. So the smaller nu, the more weight in the tails. Okay, so I encourage you to play with to see what happens and compare it to the normal distribution. The chi-square distribution, I'll let you read it, but it comes from computing squares of the standard normal. So that, and the Fisher-Snedeker is ratios of variances. So things that when we compute the variance of one quantity and the variance of another quantity, the ratio of the two is F distributed. Then finally, there is some fancy distributions like the gamma, beta, and Laplace. We need them at some point in chapter 5, but I don't want you to, instead of introducing them later, they're the high-end distribution. What do you call those? Bonus stuff, fancy stuff. Probably if you don't know this formula, nothing bad will happen to you. We'll use them strictly as visuals. Like if we want to put the distribution on some parameter that looks like this, we can choose this distribution with appropriate choice of parameters. So we'll really come to these in chapter 5. But here are the definitions, just so you have a picture of the distributions. This is very important. The transformation taking the standard distribution, like the standard normal, multiplying it by a scale factor and adding a location allows us to relate many distributions. Together they're called the location scale family. And the normal location scale family, students t location family, and the chi-square distribution is just a scale family. Okay, and completely optional reading, but there's some really cool relationships between the distributions. In fact, the reason why I show gamma and beta is to make sure this graph is complete. I'll let you read that on your own. You're not responsible for knowing all of these. I'm just showing you that these distributions are like describing different types of randomness. And in the limit, or in some special cases, one distribution becomes the other. That's it. We already talked about this in 2.3, but I want to show it to you one more time. This is an amazing site. If you have time, spend some time when you're done with this, with section 2.6. Come to this site, you will see all the distributions we talked about in 2.3 and 2.6. They're all in here. And the relationships are really well explained. If you click on a link, you will see the formula and the explanation how exactly the two are related. The graphs I'm showing here are a subset, some of the most important relations, but if you look at the website, there's a lot more. Okay, to conclude, you're not responsible for knowing all of these. Let me look at the graph. You're supposed to know, I expect you to know. Wow, I scrolled very far. I expect you to know the graphs. So I want you to visually be familiar with all of these distributions, that they exist and have different shapes. For the details, we'll see them, this one in chapter 3, these three in chapter 3, and the other ones in chapter 5. So when we get to them, we'll explain what they're used for in statistics. But for now, just look at the pictures. All right? Peace out.